So, good afternoon, everybody. My name's Mark Johnson. I'm from the Institut Langevin, the ILL. You heard this morning several times from Brigitte and from Astrid. So I've got two jobs this afternoon. The first one is to chair the session, and the second job is to give the first talk, which is on neutrons and their interaction with matter. What I want to cover in the next hour is neutrons and their interaction with matter. So the first bit of this talk is about the history of neutrons and nuclear reactions, nuclear physics, if you like. And then we'll follow up with a bit about the production of neutrons. So as we heard this morning, this is nuclear reactors, and more recently, a type of source called a spallation source that produces pulsed neutron beams. And then the third and largest part of the talk is about the properties of a neutron. And as we know from quantum mechanics, light particles have a wave-like character as well. So it's a wave and a particle, and it's a uniquely powerful probe of matter and materials and processes. And then in this talk, I would normally go on to talk about instruments and how we use them to do science. But that'll actually be the job of my colleagues who are going to give the 5 half-hour talks after mine, covering diffraction, large-scale structures, imaging, spectroscopy, and then nuclear and particle physics. So they are the experts in their own areas, and their talks will complement mine and follow on from mine and give you an overview of what we can do with neutrons. Okay, so history of neutrons. So this goes back to 1932. A bit over 90 years now. And the discovery of the neutron is credited to James Chadwick. If you're a sort of a scholar of scientific history, you'll know that discoveries are not entirely due to one person and they're part of a process. But some people, like Chadwick, made seminal discoveries, and they do indeed get due credit for their major contributions. So the very sophisticated piece of equipment that Chadwick used to discover the neutron is shown on the right here. So it just looks like a piece of tubing in a wooden support. And what's inside there is a polonium source. So what you see on the left here is the polonium source, and it's a source of alpha particles. And when these alpha particles impinge on a beryllium target, they emit what was at the time an unknown irradiation. So it certainly wasn't a charged particle. It couldn't be deviated in an electric field. So the first point about this particle was that it has zero electric charge. And these particles were then allowed to impinge on paraffin wax. And as a result of that, protons were emitted. So these are charged particles, and scientists were used to identifying those. And those protons were discovered or detected in this amplifier and oscilloscope. So the experiment, it produced some unknown irradiation, and as a result of this unknown irradiation, chargeless irradiation, protons were produced. So the first conclusion was that the radiation was comparable in mass to protons and zero charge. So what Chadwick did was he worked through this process, and he understood that what was going on here was that the alpha particles interacting with the beryllium were producing a carbon atom and a chargeless particle of the approximately of the mass of the proton. And when he looked at the energy equation carefully, so here we see kinetic energy and the masses involved, he determined the mass of the neutron, and this neutron mass is slightly greater than the mass of the proton. So that was the discovery of the neutron. It followed on from lots of work by people like Rutherford, who were trying to determine the structure of the atom and indeed the structure of the nuclei, the nucleus. And then there was a real rich period of research in nuclear physics. And here we see some of the main discoveries. So in 1938, Oliver Hahn, Strassmann, and Lise Meitner, they discovered the fission of the isotope 235 of uranium through thermal neutron capture. So this is important because neutrons that are liberated in a nuclear reaction have very high energies, as we heard this morning, or there was a chat this morning about this, about 10 mega electron volts, but you have to slow them down so they can be absorbed again and create a chain reaction. So the possibility of a chain reaction was discovered by Halban, Joliot, and Kowarski. They discovered that 2 to 3, 2.4 in this case, neutrons on average are produced in a fission process of uranium-235. And then in 1942, it was Enrico Fermi who actually made the first demonstration of a self-sustained chain reaction. In the figure in the bottom right here is a drawing of the so-called Chicago pile. So this was the experiment was set up in a football stadium underneath the stands of a football stadium. And it's a remarkable construction when you think of nuclear reactors today. It included a huge amount of graphite, which actually is the moderator. It's a moderating material. A huge amount of uranium and uranium oxide, 50 tons. And it produced an absolutely tiny amount of power, so half a watt of power. Just to give you an idea how small this is, the research reactor that we've got here at the ILL, it uses 10 kilograms of uranium, and it produces 57 megawatts of power for 50 days. So anyway, of course, there's been a huge amount of progress and developments that have led to the ILL research reactor, and it's normal that it performs much better than this first demonstration of a chain reaction. So if you just go back and look at the names, you'll realize, first of all, there were numerous Nobel Prize winners in these names. Enrico Fermi was certainly one, but names that you might be familiar with because there was a Hollywood blockbuster film a couple of years ago now about Oppenheimer. And so these names have become familiar to us once again. Or if you watch the film again, listen out for all of these physicists that made their seminal contributions to nuclear physics. So on the subject of Nobel Prizes, well, of course, Chadwick was awarded one for his discovery of the neutron. And then once the neutrons were sort of put into application, neutron scattering became an important experimental technique. Well, these two colleagues from the US, Clifford Shull and Bertram Brockhaus, they made their seminal contributions. Shull for what we call elastic scattering or diffraction, structural studies, and Brockhaus, who developed inelastic neutron scattering, in which neutrons change energy with samples. And that's the way we study dynamics of materials. So diffusion processes, phonons, molecular vibrations, magnetic excitations. Another important Nobel Prize winner shown here in this car. And if I was in front of you, I'd ask you if you knew who these people are or were. So on the right in the back seat, there's Louis Néel, and he was a French physicist interested in magnetism, for which he was awarded the Physics Nobel Prize. and he has a laboratory named after him here in Grenoble. I can see it from my office almost. And he realized the potential of neutrons for studying magnetic systems. And he wanted a powerful research reactor in Grenoble. And the man sitting next to him, some of you will recognize, is Charles de Gaulle, or the president of France at the time. And so it's an interesting time. This is 20 years after the Second World War. And Charles de Gaulle was looking for a project to reunite, bring back together France and Germany. And so, as is often the case, science is a good way of doing this. And so between the two of them, they made significant steps towards the ILL being built in Grenoble and being the future European neutron source. And at ILL, there's a couple more Nobel Prizes that we're particularly proud of. So in 2016, the Nobel Prize in Physics was awarded to these three scientists, Kosterlitz, Thouless, and Haldane. And it's Haldane in the middle, who was a postdoc at the ILL when he started his important work on so-called topological phase transitions. So these are magnetic states of matter. And then even more recently, in 2022, Aspect, Clauser, and Zeilinger were awarded the Nobel Prize in Physics. So if you read here, quantum entanglement, it says of photons, but actually Zeilinger was a long-term visitor at ILL for about half of his career, and he studied the quantum properties of neutrons during that period. And that sort of informed as well the work that he did on photons. So very important people, major scientific contributions in the field of neutrons that led to these numerous Nobel Prizes that are related in different ways to the development and application of neutrons. So neutron sources, how do we produce them? They're more difficult to produce than other kinds of experimental probes that we use, for example, X-rays, but also electrons for microscopy, Raman and infrared where you need light. So the traditional way or historical way of producing intense neutron beams is fission reactors. So nuclear reactors that use the fission of uranium-235. And as we've just seen, each fission process produces about 2.5 neutrons. So one of these is used to propagate the chain reaction, and the other 1.5 neutrons are used for extracted in the form of neutron beams that we can do experiments with. So fission neutrons that we see on the right here, these neutrons here, the 3 neutrons that are produced, they have energies up to about 10 mega electron volts. But as I said earlier, they have to be thermalized or moderated to much lower energies, about 6 or 7 orders of magnitude lower in energy. And we do that by scattering from water in a reactor like the one we've got here at the ILL. So thermal neutrons are produced, these are what we call thermal neutrons, the ones that are produced by thermalization with water around the fuel element. And they're the ones that enable the chain reaction to be propagated. But what we also have in the reactor, the experiments we want to do and the neutron beams we need to use, we like them to have different energies. And so we thermalize either at lower temperature, about 25 Kelvin or minus 250 degrees Celsius, or at higher temperature, over 2000 Kelvin, or about 2000 degrees Celsius. And that produces what we call hot neutrons. So if you were in front of me, I'd ask you if you knew how we thermalize cold neutrons or hot neutrons. But I'll tell you, since we can't interact like that in Zoom, So the hot neutron source, it's a block of graphite heated to about 2000 degrees Celsius. And so that heats up the neutrons again, and we extract neutron beams from that hot source. And the cold sources are even more impressive. You probably can guess what's a liquid at minus 250 degrees Celsius. It's actually hydrogen, or in our case, deuterium. And the cold sources, they're about the size of a basketball. And so they're full of liquid deuterium at 25 Kelvin. We've got 2 in the ILL reactor. And there's a huge fridge in the reactor building that's keeping these small volumes of deuterium cold. If you think, the ILL reactor in this case, it's producing 57 megawatts of power, and inside it you're trying to keep a basketball cold at minus 250 degrees Celsius. So the engineer who does this, who's responsible for this, he says it's like making ice cubes in a pizza oven. So that's a joke, or that's that engineer's joke. I hope you appreciated that. An idea of flux. So the ILL produces one of the highest neutron fluxes in the world, 1.5 times 10 to the 15 neutrons per square centimeter per second. The ILL reactor actually produces the most intense neutron beams in the world. So these are the neutrons that we actually extract from this core flux into beams that we can deliver to instruments. And so this is 10 to the 14, 10 to the 15 is what neutron reactors will produce in terms of flux. And then spallation is something that we've heard about from Astrid in her talk. And so this is a different way of producing neutrons. It's not a nuclear reactor, so it requires a proton accelerator, a high power proton accelerator that accelerates protons to high energy, giga-electron volts. These are then traveling close to the speed of light, and when they impinge on a heavy metal target like tungsten or mercury, they will eject a large number of neutrons, about 30. So these are the main 2 ways of producing neutrons today, or let's say intense neutron sources. And when we really do need the most intense neutron sources we can produce, as you'll see in a minute when we get to a comparison with X-rays. So this is the development of the performance of neutron sources on the vertical axis as a function of time. So going back to the discovery by Chadwick in 1932, the development of nuclear reactors from the 1940s onwards, and you can see that the thermal neutron flux has plateaued. ILL's just above this line here, and then we've got more recent continuous sources, SynQ, which is actually a spallation source, but it's a unique spallation source in that it produces continuous beams. And FRM2, the most recent neutron source in Europe. And then more recently, since the 70s, we see the development of pulsed sources, and in particular spallation sources. And again, this morning, ISIS was mentioned. It's the source in the UK near Oxford, and SNS at Oak Ridge in the US. And what's coming, and what we're all looking forward to very much, is the European spallation source. And this should have the highest effective thermal neutron flux. I should say for pulsed sources here that we're looking at the flux in the pulse and not the time averaged flux. ESS, when it's operating to full specification, it will have a time averaged or time integrated flux that's comparable to the ILL. Obviously, a neutron reactor, it produces continuous beams of neutrons. The beam is always on, whereas the pulsed sources are actually off for most of the time. So this is a closer comparison of a reactor source. So the brown line at the bottom of this plot here close to zero is the ILL. It's the brightness of the ILL source operating at 57 megawatts. And then we see the other pulsed sources that I've just mentioned, ISIS, which has 2 target stations, SNS, a higher powered source, which produces more intense pulses, and a similar source in Japan called JParc. And what you realize is that these are what we call short pulse sources. They produce pulses that are short in time. And what will be unique about ESS is that it will produce a long pulsed source. And the advantage of the long pulse being that you can then modulate in some way the beam to optimize it for the particular kinds of instruments and experiments you want to do. And the dark blue curve, or the continuous blue curve, it will be the performance of ESS when it reaches initial specification, but it's designed to operate not at 2 megawatts, but at 5 megawatts. And when it reaches that power, it will produce a neutron brightness that's about 25 times higher than that of the ILL. However, as I said earlier, what you don't see in this plot of pulses is that you don't see when the next pulse comes. So ESS will have operated a frequency of 14 hertz. So the pulse is off for about 60 or 70 milliseconds, and it's on for 4. The point with all of these pulse sources is that they're off most of the time and on for a relatively short time. And so they exploit those intense bursts of neutrons very effectively. Whereas the instruments around a continuous source are designed to use those continuous sorts of neutrons. And Astrid said this nicely this morning. She said that these are complementary sources with complementary instrument suites that do similar science in many cases, but in some cases rather different science as well. So the image you see in the top right here is the ESS here in the foreground with its proton accelerator here. So this is the target building and instrument halls. And just behind it, actually, you see the max force synchrotron. And just to situate this geographically, this is southern Sweden. And there's this apparently in the background here is the bridge over to Denmark and Copenhagen. So, okay, a quick comparison with X-rays. X-rays, synchrotron X-rays, it's a remarkable technology. Most of you will have heard of Moore's law, which is the way that computing power has increased over time. Well, synchrotron X-rays is one of the few technologies that actually has developed more quickly than Moore's law. So it is absolutely stunning, the development of these X-ray sources. And here you see on a logarithmic plot from the first X-ray tubes up to sources like what's called the extremely brilliant source at the SRF, and you will have heard about this morning. So many orders of magnitude improvement in performance. And neutrons from the very best sources like ILL, ISIS, SNS, ESS to come are somewhere actually down here at the first generation synchrotron sources. You have to look carefully at the units on the vertical axis here when you make that comparison. So I said earlier, we really do need to have the most intense neutron beams we can possibly have because the flux of neutron sources from neutron sources is inherently low. However, there are advantages to that. You can usually turn most things to your advantage. And this photograph actually shows what's called a small angle scattering instrument. It's this red tube here in the top half of the photo. And this nose that I'm highlighting at the bottom, it's the neutron beam coming from the reactor. And we see a sample here in the middle. And so what we're able to do, because X-ray lab sources have also become very powerful, the count rate on a neutron instrument's comparable to the count rate on a very good lab X-ray piece of equipment. So what we see horizontally here, this is an X-ray source on the left and a small angle X-ray detector on the right. So we can do in situ X-ray and neutron scattering. So at the same time, we get from the red detector system a small angle neutron scattering curve, and from the blue detector on the right, we get a small angle X-ray scattering curve. And we've done something similar with neutron imaging, where we do simultaneously neutron and X-ray imaging. So the neutron is a particle of the nuclei. That's what that was the importance of discovering the neutron, because it allowed us to understand the structure of the atoms, and in particular the nucleus. But the free neutrons that we produce in nuclear reactors or spallation sources, they're actually unstable, and they have a finite lifetime of about 15 seconds. And actually there's a dilemma there, really, because depending on how we measure it, we get two different answers, and this dilemma is being resolved with further experiments. So the neutron decays, as I said, it's a slightly heavier than the proton, so it can decay into a proton, and it does this after about 15 minutes. It produces also an electron and an antineutrino, and that's what you see on the Feynman diagram on the right. Anyway, 15 minutes is plenty of time for us to do our experiments. As I said, neutrons, they're certainly particle-like. They have the mass of a proton, approximately, but they also have important wave-like properties, and that's absolutely crucial to the way we use them to do our experiments. So there's the mass, charge 0, as I said at the very start. Very important. They have a spin, a magnetic moment, so they're spin half particles. So they have a magnetic moment which is comparable to that of the proton and about 1,000 times smaller than that of the electron. And this is going to be very important when we want to use the neutron to study the magnetic fields, the magnetism of materials, because those magnetic fields arise from the unpaired electrons in materials. So it's this neutron-electron magnetic interaction that's going to be of great use there. So because neutrons are particles and waves, well, they have properties that we can characterize: velocity, kinetic energy, temperature, wave vector, and wavelength. So those quantities are related by quite simple formulae here. Kinetic energy, temperature, the wave vector k, the wavelength lambda. And one relationship that turns out to be particularly useful is the so-called time of flight of neutrons over a given distance. So these are particles traveling with well-defined velocities if we've monochromated them precisely, if we've selected a precise energy. And so this is the formula here, which relates the time of flight to the distance covered and the velocity of the neutrons. So a 1 angstrom neutron will take about 253 microseconds to cover 1 meter. And so we use this timing to measure the energies of neutrons, either incident on a sample or scattered from a sample. And so typically our instruments are several meters in size, and that allows us to measure these times of hundreds of microseconds precisely. So I spoke earlier about the different kinds of neutrons or their classification in terms of their energies. So here we've got the neutrons produced by the reactor or the spallation source, and then thermalized or moderated to lower energies: hot neutrons, thermal neutrons, cold neutrons, and ultra cold neutrons. Each time we're losing about an order of magnitude or 2 in energy. The thermal neutrons, we can see here that they correspond, they span the room temperature scale. The wavelengths, this is very important, they vary from a few hundredths of a nanometer down to several tens of nanometers. So this means that they have exact, they cover those key distances in materials. So a tenth of a nanometer or an angstrom is about the length of a chemical bond. And several angstroms is the distance between molecules. And molecules can be several angstroms or nanometers in size, and macromolecules are bigger. So you can see here that these wavelengths are perfectly suited to studying matter and materials. And these energies that you might not be so familiar with, but they really do correspond to, with hot neutrons and thermal neutrons, the vibrational energies of materials and phonon energies and energies of magnetic excitations. And then when you go to lower energies, well, then you can study diffusion processes like the fluctuations of proteins that are essential to their function. One thing that's interesting is that thermal neutrons, they have a velocity of a few kilometers per second. But when we slow them down to what are called ultra-cold neutrons, then they're traveling almost at walking pace. We can slow them down to a few meters per second, and we can essentially trap them inside a bottle. So that's an overview of neutron energies. This is one of our scientists actually at ILL, and he's very happy because this is a new so-called cryogenic ultra-cold neutron source. So this horizontal tube here is actually a volume of helium-4, which is maintained at 500 millikelvin. And this is quite a challenge because this is done for 50 days at a time, so which corresponds to the length of an operating cycle at a facility typically. So it will continuously produce ultra-cold neutrons for 50 days. So here we're using helium-4 at 500 millikelvin to thermalize the neutrons. So as a probe of matter and materials, so I've just said wavelengths on the scale of interatomic or intermolecular distances, typical distances in condensed matter, angstroms, nanometers, and beyond. This equation here, I'm sure you're all familiar with it, is it's Bragg's law, which relates the wavelength of the radiation to the interatomic spacing, or this spacing between scattering planes, and the scattering angle. So it's this equation that we're going to, that's going to be the basis for the understanding of the structure of materials. And then, as I said, the energies that we've just looked at, they really are the energies of structural and magnetic excitations and diffusion processes in materials. And the other thing about a neutron, because it's not primarily it's going to interact with nuclei and not with the electrons. For magnetism, it will interact with the electrons, but let's call that a secondary interaction. And so it's highly penetrating. A neutron beam will travel through 30 centimeters of aluminium. And of course, the flux is low and the energy is low of neutrons, so they don't cause any radiation damage. Here's the comment about the magnetic moment. It's a huge strength of neutrons, and it's this magnetic moment of the neutron that's used to probe magnetism from unpaired electrons in materials. So a quick word about the importance of the neutron actually being a wave as well as a particle. If we just look at the numbers very coarsely, we've got 10 to the power 15 neutrons per square centimeter per second in the reactor core. But when we get to an instrument where we've selected out a particular wavelength band and transmitted those neutrons through a neutron guide system, we end up with a much lower flux, about 10 to the 8 or 10 to the 9 in the best cases, neutrons per square centimeter per second. But the length scales and time scales that are relevant to us, bearing in mind, for example, the velocity of neutrons, how long the neutrons spend in the material, it might be micrometers and microseconds, and therefore we will have 10 to the minus 6 neutrons per micrometer squared per second, per microsecond. Or if we go smaller to the nanometer scale or the nanosecond scale, it's 10 to the minus 15. And the point here is simply that by many, many orders of magnitude, we've only ever got one neutron in a scattering volume in a sample at any one time. So if we want to study the structure or the dynamics of that material, we need to invoke the fact that the neutron is a wave and it's going to be able to interact with a whole volume and deliver information on that whole scattering volume. And it's one neutron at a time that does that. And that's illustrated here on the right. So here we've got a neutron source emitting spherical waves. A long way from the source, we approximate these with plane waves. So this is the plane waves of one neutron, and it's going to interact with all of these scattering centers, and it will produce a scattering pattern, which is detected away here from the sample on the left. So I said the neutrons interacting primarily with nuclei. The nuclear size, again, this is a question I'd ask you, it's femtometers, whereas we're talking about neutron wavelengths that are nanometers typically. So basically the nucleus, the nucleus is a point scatterer, so we have what's called S-wave scattering, so it's just scattering from a point, and this is illustrated on the right. So the scattering power of an atom is characterized by a scattering length B. This is measured in, or this is quantified in femtometers, and it determines the number of neutrons that are scattered per second per unit solid angle. So that's illustrated here. So this is the scattered wave, amplitude B, and the number of neutrons scattered into this solid angle is B squared. And therefore the cross section is 4 pi B squared. So it's not very interesting, of course, if a neutron's only going to interact with one kind of atom or one atom. We want to scatter from a set of nuclei. So again, we have the same picture as we had before. And then the number of neutrons, this differential scattering cross-section, is determined by a simple generalization of what I've just shown you, where we have the scattering lengths of pairs of atoms, J and K, their relative positions, or their positions, so you can determine their relative positions, and that's the structural information we want to extract. And Q is this difference between these initial and final wave vectors, and they're illustrated. There's the incident wave vector, the final wave vector that takes us to the neutron detector, and in blue the Q vector, the momentum transfer vector. So that's the quantity that's going to enable us to determine this structural information through this difference in positions Rj minus Rk. So we're interacting with a set of atoms, and here there's an important difference with X-rays. Neutrons are scattered from nuclei, and so different isotopes will scatter neutrons differently. So we'll see in a subsequent slide that the scattering of neutrons from hydrogen or deuterium or tritium is different. But when you have a sample with naturally occurring amounts of isotopes, well, you have a random distribution of those isotopes in your sample, and that causes sort of decorrelates the scattering, or causes incoherence in the scattering. But the same is also true due to the nuclear spins of the atoms in your material. So they can vary too, and so you can have spin coherence and isotope incoherence. So what we see, so the scattering length depends on spin and isotope. For a material we can determine the average scattering length, B here, and that determines what we see in the first term of this expression here, the coherent scattering from the material. So this is the information that will tell us about the structure of the material. But the incoherent scattering, it gives a background which is shown here, and this has an amplitude which is determined by the deviations of the scattering from average, and it can tell us useful things like the number of scatterers that can be important. And also, as we'll see, incoherent scattering can be useful to study the dynamics of single particles. I think that will come in the spectroscopy talk later. So just one more slide about incoherent scattering. So the incoherent scattering will be zero if you have a single isotope and the nuclear spin of the atoms in your material is zero. If you've got a single isotope but a non-zero nuclear spin in your material, well, there are two scattering lengths, B plus and B minus, as defined here. So this is the coherent. So this is B plus and B minus, and this gives the average scattering as shown here, and the deviations from average, which gives us the incoherent contribution. And so often we'd like to introduce the incoherent scattering background, and we can do this by polarizing the nuclei. We can put them in a magnetic field and then cool the sample so that we're in the lowest Zeeman state. That's something that's possible but not done very often. You need a very big magnetic field and very low temperatures. Or we can use polarized neutrons, which allow us to separate coherent and incoherent scattering. And you can also use isotope substitution, and I'll come to this in a minute, and we'll see how these different scattering properties of nuclei can be used to our advantage. So scattering lengths. So why do we use neutrons then? So you might say, well, flux isn't very high. So, well, the good things, the right wavelengths to study matter and materials, the right energy to study matter and materials. But X-rays got that as well. Neutron fluxes are low. Why don't we just use X-rays? So the first bit of this plot shows the way X-ray scattering power increases as you go through the periodic table with an increase in the number of electrons. It's the electrons that are scattering X-rays, and that's why actually you don't have any incoherent scattering with X-rays. But with neutrons, it's completely different. We have an almost random variation of scattering length, as shown here in green. And so, for example, you can see that carbon's just as visible as nickel or lead, where with neutrons, whereas carbon and lead, or carbon's barely visible in the presence of lead with X-rays. And then there's another dimension with neutrons here. As you come downward, you see, for example, titanium's got numerous isotopes with very different scattering cross sections or scattering lengths. And these hashed spheres, well, they indicate the fact that scattering lengths can be positive or negative. So that's shown here. That relates to the change in wavelength of the neutron, the change in phase of the neutron wave upon scattering. So in most cases, it's positive. In a few cases, it's negative. And so if we look here at the first elements in the periodic table, this is taken from the NIST, National Institutes of Standards and Technology. They tabulate the neutron wavelength, neutron scattering length. So here the coherent scattering length of naturally occurring hydrogen is negative, but that's because it's dominated by hydrogen. But deuterium, which is present to the percent to the 1 in 10,000 level, actually has a positive scattering length, and that turns out to be very useful. So scattering lengths, positive or negative, and again, they depend on the isotope. We should also hear what's interesting with helium, two isotopes of helium, they have similar scattering properties, but very different absorption properties, as you see on the right. Helium-3 is a very strong absorber. Helium-4 doesn't absorb at all. Lithium, positive and negative scattering lengths for the two isotopes, 6 and 7, very different absorption cross sections. 6 absorbs a lot, 7 almost not at all. And then we've spoken a bit about coherent and incoherent scattering. Most of these atoms shown here and their isotopes are coherent scatterers. But what you see here from the bit I'm highlighting is that hydrogen is a very strong incoherent scatterer. So this turns out to be very useful for looking at things like proton diffusion in fuel cell membranes, but also fluctuations of proteins when understanding their biological function. The fact that they're positive or negative, when you're scattering from a randomly organized set of atoms in a scattering volume, which is typically of the order of a micron, then simply you're going to add up the scattering from those atoms, and the positive and negative terms can cancel. So that causes something that allows us to do something called contrast matching. And so what we see here is the effective scattering length density as a function of the amount of heavy water, D2O, that we put into H2O. So if we take about 10% D2O in H2O, the scattering length is 0. The water is invisible to neutrons. The scattering from that mixture of water there is no scattering, no coherent scattering. So this is making waters invisible. That's good. That's what you would do in this experiment here, where we've got a protein in red and a bit of DNA in blue, and we want to see the structure of this complex, and we don't want to see that with a strong signal from water. And so we use this magic combination mixture of H2O and D2O, which is transparent, and then we just see the solute. But what you can also do is, for example, we can tune the water solution to, in this case, I said it's DNA, so it would be up here, it would be about 60% D2O in H2O, and then we can only see the red component, which is the protein. So this is a very powerful way of highlighting parts of a complex system in solution, which is their naturally occurring environment. And the last experiment, of course, you can do is you can contrast match to the red component, which is the protein. So that would be about 40% D2O here in H2O. So a word about absorption. It's really important. We need neutron absorbers in instruments. We're also going to use them in imaging, and I'll show you that in a minute, but also in detectors. And again, X-rays, it tends to be a fairly monotonic process as you go through the periodic table, but neutrons, again, it's almost random with some very strong absorbers like cadmium. There's gadolinium as well, but also some light elements, helium, lithium, boron. And again, we can choose, depends on isotopes, so choose your element and isotope to your advantage. I would then ask you, how do you detect a neutron, which is a neutral particle? It's not trivial, and the way we do this is actually to use a neutron absorber and measure the resulting signal. And the one we use in many cases is helium-3. So it captures a neutron, it produces tritium and a proton, and it's this proton and this energy that causes a cascade of charged particles in the detector that we can measure. So helium-3 is there's no natural production, or it's not a natural resource on Earth. I think there's some on the moon. So we'll be going there soon and we can bring some back. But this scientist here, who's a normal-sized person, so he's almost 2 meters high, he's admiring the neutron detector in his time-of-flight instrument, IN5 at the ILL. So you can, this neutron detector, it covers an area of about 30 square meters, and it has about 1,000 liters of helium-3 in it. And helium-3 costs about 2,000 euros a liter. So 2 million euros of helium-3 in this neutron detector. Fortunately, because the neutron flux is very low, we don't actually use, we do use the helium-3 up because it becomes tritium and so on, but we're only using a tiny amount of it. at a time. So in the lifetime of an instrument, we really don't consume in any significant way the helium-3. So let me finish with illustrating absorption. So when we do imaging, we're often in the most common case looking at the attenuation of a beam through a sample, and that the main process is absorption, but it can also be scattering. And here we see the real complementarity between neutrons and X-rays. So this is a traditional camera which has plastic parts here. This would be where the traditional film was reeled onto it, and plastic is a light material, carbon, hydrogen, for example, and that doesn't transmit neutrons where it does transmit X-rays. And the central part of the camera is made up of metals, and that is sort of not transparent to X-rays, whereas it is to neutrons. So you see you get two completely different images using neutrons and X-rays, which is extremely useful to combine both. One more example. So this is a lithium battery. So it's a typical Duracell cylindrical battery. So they have these spiral type electrodes. I think it's manganese oxide in this case that you see here with X-rays. Beautiful data, shows cracking of the electrode from manufacturing, and then this gets worse when you discharge the battery. So you see the mechanical effects of charging or just discharging in this case as you go left to right. And then what you see with neutrons, of course, it's a lithium-ion battery. So you see the lithium, which is the other electrode, and lithium in the electrolyte. So that's what all the white bit is in this image. So neutrons complete this wonderful image you get from X-rays. We say that X-rays gives you the structural image, the structural data, and neutrons tell you about the electrochemistry. And something very simple that you see here is the electrolyte in the center of this battery is used up during discharging. And here we see the electrolyte sort of being consumed during the discharging process. Just to lead into the next talks, neutrons have got a range of wavelengths and energies. So that means that we can study about 10 orders of magnitude or 15 or even more in length scales. So when we're doing particle physics, we're looking for dark matter. So we're thinking about galaxies, but let's be a bit more down to earth. With imaging, we might be on the meter to centimeter to millimeter and down to micron scale. And then we're looking at cells and viruses, polymers, magnetic structures, atomic structures. And when we do nuclear physics, we're going down to femtometers. So a huge range of wavelengths. And similarly for timescales, we can measure molecular vibrations on the femtosecond timescale, and then we can follow diffusion processes out to the microsecond, and then look directly with, for example, imaging, stroboscopic measurements. We can look on the millisecond timescale and then beyond. And to do that, we have not just one instrument, we need a whole range of instruments. This is the layout of the ILL that Astrid showed this morning. There's actually about 50 instruments around the reactor here at the center of the reactor building. In green, you see thermal neutron guides. In blue, the cold neutron guides. There's 3 red beams in the middle, which are the hot neutron guides. So this is what my colleagues following are going to tell you about, how you use these instruments to cover the length and time scales of materials and matter that I've just alluded to. So to conclude, neutron interaction primarily with nuclei. It's a short range interaction, so no form factor that you've probably seen with X-rays. Scattering length is positive or negative, gives us contrast variation. Strong isotope dependence gives us selectivity. Coherent and incoherent scattering both have strengths and weaknesses. Scattering very different from X-rays, and that truly is a complementarity to be fully exploited. Neutrons are a gentle probe, no radiation damage. Magnetic systems, Navid will tell you a bit about those, I'm sure, in the next talk. This is a true strength of neutrons to study magnetic materials. And then this huge range of length and time scales that we can study with neutrons. These are some references. You'll have access to all of this in due course. So it's really nice to have such a lot of people online for a virtual training session. But of course, you really have to come to the facilities that have been mentioned to you earlier. Sometimes you can kill two birds with one stone and come to a neutron and an X-ray facility. It's the case here in Grenoble on the European Photon and Neutron campus, but it's also the case at Oxford, at PSI, at Lund in southern Sweden.